Hey guys, Joe Pye here at Advanced Innovations. Welcome back to the shop. The next piece in line is the Eccentric strap. This is the arm, very much like a connecting rod. I guess you could call it a connecting rod, but that's not what they call it. It is an eccentric strap. This drives the valve in and out of the steam chest. Actually, this drives the rod that drives the valve in and out of position in the steam chest. Now we're on track. All right. Well, I think the first thing to do is remove any flash lines on here that you find unruly or just not up to your liking. And it looks to me that the parting line on this is off center. You can see very clearly that that particular flash line appears to be a little further to one side than the other, and that would be supported by looking at the amount of material present here versus here. That's an interesting observation. First thing I'm going to do when I clean these up, I will run these across the piece of emery and get these to be a parallel configuration. And then I'm going to squeeze them in a vise, mill these sides off so that they are parallel and reliable and square. And then I can go into aluminum jaws and do the pocket work, do the facing, and anything else that needs to be done. I considered doing this in, on, around, near an expanding arbor in a lathe. That seems like a very possible way to do this thing. So, it's spinning around. You could face it off, flip it, of course, face off the other side, but then that's pretty much the end of whatever you're going to do. At least holding it in a pair of jaws. Gonna have to come up with some kind of support here so this doesn't go all diving board on you. I did manage to straighten it out to a point where I am confident that I'm going to be able to clean it up and look good. So the first thing I'm going to do, and as I've been told, don't bother with the filing. Seen it once, seen it 1,000 times, right? I'm going to clean it up, and I'll show you what it looks like before I put it in the machine for any type of machining. Let's make all the ugly go away. All the surfaces that will remain as cast are blasted and finished off. This surface, these two surfaces, this back surface here, both of the edges, they're going to get milled off on both pieces. Then the bores, holes, thinned out, drilled, tapped, split, done. Simple. Let's go over to the mill, pick a side. I've got one side shined up, and that is the down side for the first stop. That will be my orientation side, and I will use a ball in this hole because I can't guarantee these surfaces are parallel. So I'm going to pick a driving surface, and that's the one I'm going to stick with. Both sides. Let's do it. This is the exact same setup that will be used to bring the end feature here to its final thickness, but not used for the bore. Having established two parallel surfaces, two sets of parallel surfaces, I can now measure this and find out where it is in relationship to this arm. I want this arm in the middle of this casting when it's done, just for visual appeal. Then I'll clamp it down to a plate and we'll finish off this end, but that's got a lot of movement down there. It's a very flimsy little part. I will bore it in this same setup. I will set up a stop and bore it so that we have a plug that I can stick in here. And go from there. Take it over to the plate, check it out. Now once I've inspected both of these pieces, I did create a sheet telling me what all the values are based on what side and what part. I then have a choice that I can either remove all the material necessary to straighten it up and go a little off center with where I can cheat, or I can put it back in the machine right now, clamped exactly the same way it was, and influence the setup to put this tip where I want it and change the parallel relationship of these two surfaces. They'll still be parallel, but they'll be moved from this orientation into a little bit of this orientation to accommodate for the bend of the part. I have to sit down with a calculator and see what values they really show about these two pieces. They're perfectly fine. They will work. There's no question about that. It's just going to take a little planning to make sure that everything comes out where I want it. Next operation line is to thin the tip of this out, and for sake of just saving some time and making sure that it's as symmetrical and equally centered about the end, large end, as possible, I'm going to do it in a little unorthodox manner, but hope you can follow along. I'm going to climb cut both sides with one setting of the vise. So I'm going to take the piece out and reverse it and do the exact same cut on the other side. Now with the rotation of the cutter going the way it is, when it encounters this piece, it's going to drive it this way and have less of a tendency to want to suck it into the cutter. If the cutter was on this side of the part coming down this side, it would have a tendency to want to pull this in. So our rejection is better than pulling it in. Pulling it in is going to leave nasty chowder marks. The rejection may bounce a little bit, but for what it is, I'm going to do it this way. Then I'll strap it down and drill the holes. And most important, I'm using a very small diameter multi-flute cutter. It's a 4-flute 1/8 diameter cutter, so that the distance between the flutes is very small. As it comes around, it'll have a tendency to maintain pressure on the part and keep the part from bouncing aggressively. If you were to do this with, let's say, a 1/2 inch 2-flute, the incremental contact between the cutter flutes would give this a chance to rebound from any movement and cause a much greater dig as it cut. So we can expect good results this way. Now we can do it. If this part were any longer or any thinner, I would probably not do this, but I trust it because of the geometry of the part. This is a very reliable setup to give you a symmetrical part, but does depend on the end of the part, the large end of the part being same from piece to piece. So if you're doing multiple pieces, creep up on the final dimension so you don't get burned. Using a couple of gauge pins mounted in the drill chuck, I go for a visual alignment on the front boss, since that is the one that you cannot control. That is officially in place, and any lack of concentricity would probably show up pretty bad. Now, if you look at the leading edge of the pin, it looks like the pin is a little bit out of alignment. Watch the shadow affect that. Pulls it right in. When my finger blocks out the glare, it looks a lot better. Anyway, that is 0, 0. Using another pin for the backside boss, moving the distance called out on the print. We're well within the boundaries of the part. That is a rough cast feature. So if it's a little bit off in the back, well, that's going to be trued up real quick here as soon as I put the boring head in. That is the next stop. Let's do it. The advantage to strapping it down to a plate like this is you reduce the risk of distorting the hole during the boring operation. If I had this positioned in the same format that I milled it in, squeezing it in a vise, you could easily bore a round hole, but risk elongation of that feature when you release the pressure of the vise. It is always best to clamp the part in line with the axis of the feature. Clamping it any other way, you risk distortion. And the first piece always takes the longest. Using an adjustable parallel like this, if I squeeze this too tight, it's going to elevate this and the hole may come out skewed. Keeping it somewhat loose, the danger is when the drill breaks through, this turns into a helicopter and it doesn't end well. So I'm going to try to offset this block as far as I can to get out of the way of that hole, yet still offer support underneath. So if it looks like it's a little off-center, it's going to be off-center intentionally. Next feature is a hole in the bottom, and I will show you what that's for in the future. Off camera, this part was set up with indicators and edge finders to put this hole exactly where I wanted it. It's a simple 1, 2, 3 block and my little tooling plate set on a parallel, so I have the projection that I need. The part is longer than the vise allows to grip vertically. These holes are not being used as intended, but they are still capable of being tapped to the 7BA thread. Change the setup slightly, put the oil holes in, and this piece is done, believe it or not. And when I said done, I actually mean done. I'm not going to split it. I'm not going to put the hardware on this side that they've recommended, at least not yet. Before we move on to part 43, you may have noticed that in the manufacturing, in the fabrication of this rod right here, I left this entire feature off, as well as changed up a little bit down here. This is a through hole now. It's not a threaded hole, and this is completely gone. There's no hole, there's no split, there's no bolt, there's no double nuts. That is just completely wiped away. This little grub screw right here is so small that the torque that you'll be able to get on this to keep this eccentric spinning is going to be extremely limited. And, you know, in my opinion, it's just going to potentially fail. If there's a weak point in this design, it is the drive feature for this screw right there. If you have an available cap screw, if you want to sacrifice one of these and put it in here, fine, make this a little bit longer, use one of those. But make sure that when you do that, you put an appropriate undercut on the outside of the crankshaft so that you don't scar up the crankshaft and you can get this off. I've decided to keep everything enclosed within the crank rod. I am going to modify this guy right here. I'm going to put a much larger screw inside the crank eccentric, or inside the crank arm eccentric, so I can use an Allen key to drive it down. Okay, well, how are you going to adjust it there, Mr. Genius? Well, let me tell you. When you rotate the crankshaft, the hole that drives that set screw or cap screw, not a set screw, grub screw, is going to rotate and align with the hole in the end of the crank arm. So you just simply insert your Allen key through the end of the crank arm into that set screw, unloosen the set screw. Yeah, I had to say it. Unloosen the set screw, rotate the crank a little bit, tighten the set screw back up, remove the Allen key, and when it spins, you don't see anything except the outside of the eccentric going round and round. Yeah, I'm just going to give it a go. Worst comes to worst, I can always revert back to the original design, but we're just going to go with that for now. The intent of the original design is this little guy down here. This is a 1.5 millimeter nub turned on the front of a 7BA nut or 7BA screw. That little protrusion right there will come through the inside of this arm and engage this slot right here. That is what keeps the crank arm from sliding left to right. My eccentric sheave, my eccentric collar will have a shoulder on both sides, an additional plate on this side held on with cap screws. I think you'll like what you see. I'm going to go with it. There's a dozen different ways that you can modify that, but that is the way I'm going to do it. Let's do it. This is the diameter that will ultimately spin continuously inside the eccentric strap. So make sure you have a nice clean fit on that. You don't want it to jump around too much, and you certainly don't want it too tight. That would be a recipe for disaster. Located in a vertical V-block setup, I'll tram the part to read 0. Set my digital to 0. And now offset the 093 on the print. This is the eccentric hole that will engage the crankshaft. Drilled end board. Nice fit on this. You don't want this wiggling out. Any difference between the size of this hole and the size of the crankshaft that it locates on will add to the eccentricity value that you've machined into the part. Because when you tighten down the retention feature, whatever your retention feature is, it'll kick it that much further off center. The cap will be retained by 172 cap screws. And be very careful when you tap these. That 172 is pretty small. Mill work is almost done. Going to go back over to the lathe and part this off. With a 3/4 collet in the machine for the parting operation of this particular component, I'm going to seize the moment and take this opportunity to face off and chamfer the top of the cap that will be needed to complete this assembly. Bring in the facing tool and clean this face up right now, put the chamfer on it. Then we'll move over to the, actually no, we're going to change the collet out and flip this part around, flip the original part around and face the back off for cosmetics. The final flange thickness I elected to use is 060. It's about 1.5 millimeters, and with a small 45 chamfer on the outside edge. Back to the mill. These operations are almost identical to the eccentric driving section of this assembly, but these holes are not tapped. These are through holes. And if you want to take a little bit of liberty with the size of the bored hole, it doesn't have to be as precision as the other one because the work is already done. This cap will be retained by 172 cap screws. Like I said, there's not a whole lot of pressure on these, so a small screw is sufficient. Going back to the original component, I put the 172 cap screws in the cap, and I'm using those as locators for the 90-degree side hole. And yes, this was set up with indicators and edge finders to make sure everything is where it needs to be. This is a 1/8 counterbore. It's about a 3 millimeter counterbore going about 2 millimeters deep. And this is where the small cap screw will hide inside this assembly at assembly. And yes, there's 2 of everything. If I haven't shown 2 of everything, rest assured there are 2 of everything. If you guys haven't made one of these small tap handles, I highly recommend that you add one to your toolbox. It gives great sensitivity feedback on smaller taps. Okay, let's take a look at the final components here. The eccentric hub, I changed that up quite a bit. I went for a sandwich style, like on the PM kit. I really like the way that looks on the kit, and that's just what I did. This is a hubless design. So these 2 sides are together, screwed together. That's how it looks at assembly. And now for all of you that are saying, well, how are you going to time that thing? Well, that's what this little guy here. That is not only the original 7BA thread that was on the print, but it is also an access hole. The clamping feature against the connecting rod, or against the crankshaft, excuse me. Now it's just a matter of unloosening this a little bit, rotating the crankshaft a bit, tighten this back down, and you have effectively changed the valve timing on this component. Let's take a look at what it looks like when it's all put together without boring you through the whole process. There we go. Zoom out on that. I saw absolutely no reason for putting the split in there and putting the screw and the bolt on this connecting rod here. The only reason I could see for that being there was to take up wear. As it wears, you can cinch up on the device on the outside, the nut and bolt, and close up the clevis around the journal. But also the journal only had 1 screw coming in from the bottom that rode in an undercut, and it was just not going to give me the stability that I wanted. So this is a very clean setup, and I think it should serve the purpose just fine. As usual, I thank you for spending some of your time with me today. And wherever you are in the world, I hope you're well and happy and safe, all of the above. Hey, I'm Joe Pye here at Advanced Innovations. Calling it a day. I'm out.